resistor temperature dependence in space by me, Geremie Tipsword. All right, so what is resistor temperature dependence? Basically, it's an object, a conductor, and how its resistance actually changes in accordance with the temperature, right? Which this is an interesting question when you're talking about space because there's such wild variation in temperature in space. You know, to your extreme lows, to your extreme highs, thousands of degrees next to, you know, stars or sun. So it becomes a very interesting question where you're dealing with such varied temperatures, whereas on Earth, there is varied temperatures, but not even close to what you see in space. So how you calculate the change in resistance, you're going to have a setup for that, and that R is going to be our ending resistance. That's what we're looking for right there. RO is going to be our initial value resistance, which is our starting case. The temperature coefficient of whatever the conductor is, our initial temperature, and then our heated to temperature, which is our ending temperature. So I used copper in this case, and copper is just a very common conductor. I also used 20 degrees Celsius, which is about room temperature. It's about 70 degrees Fahrenheit. And I also used 235 degrees Celsius for the end case, which is the cosmic background temperature. And 1.015 ohms, that's going to be the value of resistance at 20 degrees Celsius. So basically what we're finding with this is going to be the resistance at 235 degrees Celsius. All right, so here's the setup for the equation. And to accomplish this, we're going to take our starting resistance, our initial value of resistance, and then we're going to multiply it by the following parentheses. The 1 plus the temperature coefficient multiplied by the following parentheses. Then you take your ending temperature subtracted by your initial temperature. Then you close both parentheses. And that'll give you your answer. And here's the equation plugged in. R equals 1.015. 1 plus 0.0401, 235 minus 20 degrees. And that will give you the answer of 1.89 ohms. And I just want to point out here that this is going to be your ending one. And then if you look to your left, the RO, that's our initial. So you went from 1.015 ohms to 1.89 ohms, which doesn't seem like a huge move, but we'll do a little calculation here, and we'll see how that affects the whole system of operations of this this thing. And so this is going to be our temperature at 235 degrees Celsius, our resistance. All right. So we're going to use Ohm's Law to kind of illustrate how this is going to work. We're going to use the version that gives us the current. So we're going to have our current is equal to the voltage over the resistance. And for this, we're going to use a voltage of 2500 watts. For the reason that various different exploration probes and stuff like that have used a system, a solar panel system that took in that much power. And it's not exactly the same thing because there's a whole battery. There's various more elements included in this. But I wanted to use that as kind of a baseline of what sort of wattages we're dealing with. So when you plug that all in, you're going to end up with 2,463 amps at the room temperature. And then you're going to end up with 3,966 amps at 235 degrees. And the whole point here is just to point out the wild variance here. These aren't just two numbers in isolation. This is, as the temperature rises every single degree, though that amplitude, those amps are going to increase, that current is going to increase. And as far as I'm aware, there's no sort of system that can handle currents wildly varying. So what they end up doing for this sort of system is they're forced to control for the temperature. And that's actually why I used that 20 degrees. Oh, and of course the difference between those is 1505 amps, which is pretty substantial change. The reason why I use 20 degrees is that room temperature is generally what they use to maintain on these probes and these other devices that are sent into space. It's generally that 20 degrees Celsius. All right, I just wanted to point out all that stuff, that information. Thought it was kind of interesting. Thanks for watching.